All right, so welcome to lecture 4. So today we talk about how we can design a parallel program from scratch. And how you can implement it more efficiently. So basically what I want to cover for today is to give you a kind of thought process, a thinking process of designing your parallel programs, like how to start and how to do it step by step until you can implement it. So it's kind of very abstract guidelines for designing parallel applications, but it is usually a good starting point if you want to parallelize something. All right. But before that, let's have a short review of the previous lecture because its materials probably was one of the most important materials in the entire course. So last time we talked about latency hiding using multi-threading and also memory bandwidth problem in high-performance computing. We also talked about ISPC programming a little bit and also SPMD programming model. So let's go through them just briefly. So about the latency hiding, we saw that you can see a lot of stalls in single-threaded applications, right? So the solution was to have, sorry. So the solution was to have more execution context in the hardware, right? Like here. And using those execution contexts, we could allocate, for example, in this case, four like instruction streams, right? And when one core stalls, then you can easily switch to another core, to another like instruction stream for execution, right? So with that, we could keep the cores of the CPU, keep the ALUs always busy because they are always executing some instructions from different instruction streams. So for this core in particular, it can accommodate four instruction streams, but at each point in time, it can only execute from one of those instruction streams. So if you have four execution context, it doesn't mean that you can execute four instruction streams at the same time, but you can execute four instruction streams concurrently by switching between one to another. Okay. This is strange because my pointer, my pen doesn't really work with this first click here, but anyway, so let me change it here a little bit. Yeah, I still have the same problem, but anyway. So, and we saw that for computationally intensive applications, what we can do for latency hiding is to switch to other threads that can perform computations until you're in the same time that you're waiting for the memory. So this way, for computationally intensive applications, you can also keep the CPU cores busy as much as you can. So this was about memory latency, but when it comes to memory bandwidth, we saw that even if your program has a lot of parallelism in it, it doesn't mean that your program is able to use all of the processor's cores efficiently. Why? Because the memory bandwidth is quite limited in many modern systems. And it is so difficult for some so-called memory-bound applications to feed all of the cores of the processor with the data that is required, right? So for example, in this very simple add load example that we saw before, we could see that even though that we have a lot of cores that they can do computations, but the memory system really cannot keep up with the cores in a sense that it cannot really provide enough data to the cores for computation. So for that sort of problem, you can see that the memory system is always busy at each time steps, right? But After a while, the CPU cores they stall because they're waiting for the memory transactions to be completed. So these kind of applications are called memory-bound applications, and they're quite common in so many workflows, including machine learning. So typically, in the model training workloads, when it comes to deep learning, you have compute-bound applications, which means that the bandwidth is not a big problem. But when it comes to inference, like large language model inference, then in those kind of cases, the memory bandwidth becomes quite problematic. So that's why when you want to buy a GPU for inference, you should really pay attention to the memory capability in terms of like memory capacity and also memory bandwidth. But when you want to buy a GPU for training, probably you would look for more compute capability rather than memory bandwidth capability, right? So these are kind of different things when it comes to even buying hardware for some calculations. All right. So the main takeaway was that the computation, it depends also on the algorithm and computation, but typically the computation is bandwidth limited because of the limitations in memory bandwidth capabilities. All right. Then we talked a little bit about ISPC, which is a compiler provided by Intel that you can easily define your parallel programs, right? You can declare in your program which part of your program can be executed in parallel. So you, as a programmer, tell the compiler that this portion of my program can be executed in parallel, and then it's up to the compiler and the runtime libraries to parallelize your program. So this is what ISPC is basically doing. So it uses this single program multiple data programming model, or SPMD, where it creates a kind of different problem instances, like different program instances. So, but the same program, but with different instances. And then it executes those instances in parallel, and it's up to the program code to identify itself in order to do computations for the work that is assigned to, right? And then we saw that when we use ISPC, there are kind of different way of implementing our parallel program. We can do it ourselves, or we can rely on the ISPC compiler to do that for us, right? So based on that, we understood two very simple task assignment. One of them was this interleaved assignment, right? Where each thread, like for example, if you want to read data from this array, so each thread reads like one element, but those elements are beside each other. So they are consecutively stored in the memory. So thread one reads zero, thread zero reads zero, and then thread one reads one, two reads two, right? And for some applications, this was a good strategy because we are reading from memory uh, we are reading from consecutive locations in the memory, which helps the memory system to provide uh, data in one transaction. If you are working with the CPUs, it's going to be in the cache line. And when you are working with the GPUs, all of this data that you want to get, because they are consecutively stored in the memory, so the memory can provide this data with one memory transaction rather than going to the memory back and forth. But it also depends on the application. Another assignment that we discussed is the block assignment, right? Where you have defined a starting point and an end point for each thread, right? Defining a block of data for each thread, and then each thread will compute on the corresponding blocks, right? And for this particular application, it was not good because then you had strided memory accesses, which was not for caching and also memory coalescing in GPUs. All right. And typically, when you have such an application, you can kind of draw this table, right? And then you can analyze how the memory is accessed in order to understand if the memory accesses are like consecutive, or if they are strided, or they are totally unpredictable. Okay. All right. And then we saw that apart from that you can implement your own implementation of this parallelism. You can also rely on ISPC for each keyword, right? That uh, in this case, you just tell ISPC compiler that this for loop is independent in terms of like iterations, right? And you can parallelize it whatever you see best fit, right? And then it might have very different implementations depending on the ISPC implementation. So it can be completely serialized, right? Depending on the system, or it can implement like an interleave iterations, or it can use this block iteration, block assignment, or implement some sort of dynamic assignment. So what is very important here is to understand the differences of the abstraction and the implementation, right? So in terms of ISPC, for example, and we will see so many other programming models that have the same philosophy. So you as the programmer, you work with the abstraction layer, right? You only declare how your program is written and what portion of your program can be executed in parallel. And then it's up to the system, up to the implementation in order to execute that on the real hardware, right? So in terms of ISPC, you just declare your program, the parallel portion of your program, right? And you don't need to do something else. And ISPC decides about the vector length, like your SIMD length, and how to schedule the task into the SIMD units, and so on. So that's very important to understand this distinction between abstraction and implementation. And typically, you care about abstraction, but in order to get to get benefit from your implementation, you need to know how things are implemented in order to hand tune the performance. All right. So in terms of abstraction, ISPC follows this SPMD programming model, right? Single program, multiple data. And you as the programmer only need to think about this SPMD. When you write your programs in ISPC, in CUDA, in MPI, and other parallel programming models that use this SPMD, what you need to think about is that, okay, what I'm writing, this kernel that I'm writing will be executed on different execution units, right? You don't care what is that your execution unit, whether or not it's the hardware thread, it's like SIMD cores, or it's the entire like data center or whatever. So you don't care about that. What you care about is that your program is executed in different instances, right? And you should coordinate work with in each program. So each program needs to identify itself and knows, for example, the maximum number of programs that they are executed in parallel. And using these two pieces of information, you can kind of determine what program does exactly what, and what portion of data what program instance needs to compute. So this is one of the most widely used programming models in parallel computing, and it can be like from low level like SIMD to multi-core systems and multi-threaded programming, and also multi-processing programming, and also in distributed systems. But the thing is, as I mentioned a couple of times, this SPMD is an abstraction. So it's a programming model, right? But it can have so many different implementations. So in ISPC, the implementation goes to SIMD cores, but in MPI, it goes to like the parallel processing, and each process is scheduled on a different GPU, right? Right. So this is different thing. Okay. So we can also have even more or even higher abstraction layer, And then you see programming models similar to what you've seen, like in machine learning frameworks, like PyTorch, right? So here in ISPC, for example, then where you have this independent for loop, you need to write the for loop body, right? But you just declare that this for loop has independent iterations, and then you ask ISPC to implement the parallelism, the best parallelism strategy for you, right? But you can abstract this away even more, right? By having some sort of functionalities that you typically see in Python uh, numerical computing libraries. So for example, when you have two NumPy arrays or PyTorch tensors like X and Y, when you execute this line in Python, Z equals X plus Y, then under the hood, it can have SPMD implementation, right? It can have this line of code can be compiled into an ISPC instruction, right? Like the one here, right? So what these numerical computing libraries provide you with is these sort of very high level abstractions that you can use without really thinking about the about the internal implementations. But they are not usually enough. Sometimes you want to write your own computational kernel that is not available, for example, in these libraries. And for that, you have to write a customized compute kernel, right? And then you can write these kind of abstractions for your kernel and add it to PyTorch runtime system. So this is currently one of the high level abstractions that you can get. But it's very important to know how things are implemented in order to get performance. All right. So any questions about these topics so far? All right. So let's start today's lecture. So as I said, today we will think about the thought process of writing and optimizing parallel programs. Okay, so well, this is kind of a very abstracted guideline. So what you typically want to do when you want to create a parallel program is first to identify the work that can be performed in parallel, right? So you have a problem that you want to solve, but in the air, you should be able to kind of figure out how you can decompose your problem. What parts of this problem can be executed in parallel and what parts cannot be executed in parallel, right? So, and here you should kind of discover the dependencies. We will talk about that in more details in the next slides. And then if after you identified what portion of your program you can execute in parallel, you have to partition the work, right? And then you have to manage the communication between different portions because some portions of your program probably wants to have some communication with the other portion, and also you need to have some sort of synchronization and so on. But when you want to create a parallel program, basically the common goal which everybody thinks about in the beginning is to have speed up, right? So you want to make your program to make it run faster, and a speed up can be computed quite simply. So you just need to divide the time taken by one processor to the time taken by p processors. Okay, if you are using p processors. Okay, so this is the main goal, but you also have other goals that in some applications can be quite more important to consider. For example, efficiency. So how efficiently you are using your cores, your power and energy and this kind of stuff. But the core goal is to have this speed up. Okay. All right. So this is, in a nutshell, how you can think about parallel program design. So you have a problem to solve, right? And then using your domain knowledge, or when you discuss with an expert in that domain, you can decompose the original problem into different tasks or different works, right? And different works, in general, they can have different complexity. So they don't necessarily need to be kind of the same in terms of complexity, but it's going to be good if you can have equally divided works. But ideally, I mean, but practically, this is not the case. But also it depends on the application. So for example, data parallel applications, you typically can divide the data like equally between different tasks. But in other applications like task parallel applications, when you have really many different tasks, so this is going to be a little bit tricky. So the first step is the decomposition, right, which is one of the most important steps. Then you have to do the assignment, right? So you have different execution units, and you have to decide which task goes to which unit, right? Which unit executes which task. And this is very important, and we will talk about it in the next lecture. And then after you assign tasks to different execution units, you have to manage the communication, right? You have to orchestrate the communication between these execution units. So like probably you want to do different kind of orchestration. So you want probably have to communicate between different execution units, or you want all units to wait for other units to do something, and this kind of orchestration depending on the problem. And finally, after these steps, what you want to do is to assign is the assignment to the real hardware resources, right? So now you know how many execution units your program needs to have, how they can communicate, and also which execution unit does exactly what. And then after you have this information, you need to assign those tasks and execution units to the real hardware resources, right? And it can be different CPU cores, different SIMD units, or different machines also, and different GPUs, and this is going to be quite diverse. All right, any question about this high level understanding of this parallel program design? All right. Okay, so
I,
yep.
I wanted to comment or ask. This looks very, very similar to programming divide and conquer algorithms
Mm-hmm.
in the sense
Well,
that you,
yeah, well, it depends. Yeah, it is. As I said, this approach is very abstract, so you can have so many implementations for that, right? But conceptually, when you have this divide and conquer program decomposition, you are just adding more task in a runtime, right? You have a tree, right? And then you have your number of tasks are increasing, right? Dynamically.
yeah, of course. I mean, in the reasoning, not in the
Yeah.
execution or
Yeah.
implementation.
It could be similar, but
There,
as I said, different implementations. So you can have
yes,
a
yes,
static task assignment, you can have dynamic as task assignment, and this divide and conquer is categorized under this dynamic assignments. We will get to
yes,
that in the
yes.
next lecture, actually. Yes. Good question. All right. Any other questions? All right. So let's start from problem decomposition. Well, so it is quite simple when you want to understand it, but in reality, it's not that trivial to decompose your problem into different tasks. But the main idea here is to break up the problem into different tasks, right? That can be executed in parallel. So this is the main idea that we want to have there. And the second goal here is that we want to have at least as many tasks as possible in order to keep all of our execution units in our machine busy, right? So there are two things. We want to decompose the problem into different tasks that can be executed in parallel, and we want to have like so many tasks, right? Enough number of tasks that we can fill the machine with, right? So if you remember, if you can hide the latency, right, in multi-core systems when you have enough instruction streams in each execution context. And this allows the system to switch between different instruction streams, right? So when you want to decompose your problem into different tasks, you need to have like as many tasks as needed in order to hide the latency, right? So you should keep that in mind. But the key challenge here in the decomposition is identifying the dependencies, right? So because in so many applications, some tasks some tasks depend on other tasks, which means if you want to execute, for example, task B, you have to finish the execution of task A before B. So it ruins the parallelism, right? So it makes your program to be executed in a serialized manner. And we will see that that could be problematic even for the problems with very small amount of dependencies, right? And for that you need domain knowledge. For example, when you want to parallelize a machine learning program, you need to know how machine learning works. Or if you want to parallelize a kind of numerical simulation program, you need to know how the I don't know, differential equations work. So this is the domain knowledge that I'm referring to. All right, so let's see how these dependencies, when your tasks are dependent on each other, can affect the performance and the speed up that we want to get. So there is a very fundamental law in parallel computing, which is called Amdahl's law, Amdahl's law. And it basically says that if you have a perfectly parallelized program, right? But if S portion of that program is serialized, right? As for example, S can be, I don't know, 0.1. So if 10% of your program is like serialized, then the maximum speed up that you can get, even if you can parallelize the program perfectly without any computation or synchronization or any parallelism overhead, in that case, the maximum speed up is smaller than 1 over S, right? So this is a very important observation. So if 10% of your program is sequential, it means that even if you use theoretically infinite number of execution units, the maximum speed up is going to be less than 10. Okay? So let's see an example just to understand it better. So here I need some sort of interactions from you. So here we consider this image brightness application. So we have an n by n image, right? N by n like pixels. And then what we want to do is to multiply the value of each pixel by a number, for example, 2, right? So this is the first step that we want to do, and then we want to compute the average, okay? So in the sequential implementation, we need n squared time to compute step 1, right? Because we have to go through all the pixels and then multiply the element by 2. And then in the second step of the program, we have to go through the pixels again, right? And then compute the average. So compute the sum and then divide it by the number of pixels, right? So in total, if you execute this program like sequentially, then in this case, your complexity is 2n squared. Okay? So you have n squared time for the first step and then n squared time for the second step. All right? So now assume we have, so this is the question for you. Now assume we have P processors available, right? So the question is how we can parallelize step one. So at the moment, don't think about the step two. So if we have P processors available, how we can parallelize step one, and if we can parallelize step one, what would be the time complexity of that? Assume no synchronization and perfect parallelism. So what do you think?
We could do for each e from 0 to n squared to parallelize the multiplication by 2.
Yeah,
Um,
we are discussing conceptually. You don't need to think about the program. So what would be your strategy to parallelize this? Like for P processors, and you can assume that P is a very large number. You have up to infinite number of processors.
Then I would assign a pixel to each processor, or a group of pixels to each processor,
Okay.
and each processor.
And what would be the complexity?
The complexity would still be n squared.
Well, it is about time complexity. So if the serial program takes n squared time, and if you assign each pixel to a processor, right? So what would be
Yeah,
the time complexity of this P processor parallel execution?
maybe n squared divided by p.
Exactly. That's true. Yeah. So if you have P processors, ideally, we want to get n squared over P, right? But we know that according to the previous lecture, this is not really happening, at least for this problem, because we have this memory bandwidth limitation. So it's the memory bound application. So the ideal speed up is not n squared over P. All right.